Now we will proceed for session 2 of day 5, customizing large language models for specific use cases. It gives me immense pleasure to extend a warm welcome for this session to our esteemed resource person, Dr. Supriya Bajpai, Physics Research of India, Bengaluru. Dr. Bajpai is distinguished leader and researcher with 12 years of experience in driving innovation and cross-domain R&D. She holds a PhD in engineering from Monash University, Australia and IIT Bombay, and MTech degree from IIT Roorkee. With a strong focus on AI/ML solutions, Dr. Bajpai expert spans medical AI, computer vision, generative AI, LLM, spatiotemporal modeling, and prediction. Dr. Bajpai has secured patents and published papers in top-tier journals and conferences. This year, Dr. Bajpai represented Fujitsu in an international platform in South Korea. Please join me in welcoming Dr. Bajpai, an expert in computer vision, NLP, deep learning, and advanced data science methodologies, who will share the valuable insights with us today. Welcome, ma'am, and over to you. Thank you.
Everyone. First of all, I would like to thank
Thank you,
Bharatiya
ma'am.
Vidyapeeth College and the Dr. Deepika Kumar, ma'am, and the organizers, especially Gargi Mishra and Rakhi, ma'am, for inviting me to such like FDP program and organizing it. Thank you.
Thank you so much, Dr. Supriya, for joining us. Thank you so much. Dr. Deepika, this side, ma'am.
Thank you. So, yes. Thank you, ma'am. Yeah, so should we start now?
Yes, ma'am, we
you
can
can.
start.
Okay, so I'm sharing my screen.
Yes. Visible, ma'am. Properly visible.
Yeah, okay. I'm audible also.
Yes, ma'am.
Okay. So let's get started. So today we will actually deep dive into something that's been making a lot of waves in the tech world. That is large language models. We also know it is also known as like LLMs in short form. So these are the systems behind things like chatbots and writing tools and even the recommendations that you get from your favorite apps. Like they are based on vast amount of data and like basically text data and data in any other form like images, 3D signals, etc. and are designed to understand and generate human-like languages. So they are actually kind of like the brains behind the things like ChatGPT. So it looks like that they are brains. Just a second. Sorry for the interruption. So they look like brains, but actually they are not. They are just the trained models and on a very large data set with having lots and lots of parameters, like in billions and trillions of parameters. So what actually are just trained to predict the next word. So given a bunch of words or a sentence, they just know how to like they just predict the next word in that sequence, like which word will occur next. So how do they do that? So they are trained on large number of text data. So what happens given a vocabulary of words, so the system will predict which word has the highest probability to uh, means to be the next word in this sequence. After suppose after some prompt is given, a transistor is a semiconductor device used to amplify or switch. Now using this like switch word and also the transistor, the whole sentence, it will try to predict that which word will have the highest probability of occurrence. So it is electronic. So it is just a next word prediction model. Uh, here I'm just talking about the text only, but actually the input can be in any form, like text, images, signals, voice, and we feed everything to the large language models, and they can perform a large number of different variety of text. Like they can perform question answering, they can do sentiment analysis, object analysis, text summarization, and code generation, and many more. So the LLMs are basically trained on, if we broadly categorize it into like two main tasks. So it is understanding text and generating text. So first is understanding text. What is understanding means? Suppose I want to a person gives the review about an product. So now we want to categorize or classify whether the person is happy about the product or not happy about the product. So in that sense, the system needs to first read the reviews and understand it, like, okay, this has like what kind of sentiment it has. So in on that basis, once it understands the sentiment and the context of the of the input, it will classify it as like happy, not happy, positive review, negative review. Similarly, like named entity recognition or the part of speech tagging. So if we want to tag like which word, which words in the sentence noun, pronoun, adjective, etc. So for doing that, LLMs first need to understand like the grammar of the English, the whole context of the not context actually, it should understand the grammar and the like how English works. So it is depending on that, it will categorize. Okay, once it read, okay, it understands what is English, and then it can tell like, okay, this is noun, pronoun, all those things. Similarly, question answering, like question answering can be of many types. So understanding text is like comprehension based. So comprehension based means given a big paragraph, and now I want to user ask a query. Okay, now so the system will read the whole paragraph, extract the exact answer from that paragraph, and it will show it to the user. This is like understanding text. There is no text generation is happening. Text generation means the for example, in the question answering comprehension based system is not generating, or like it is not adding anything extra from its own side. It is just extracting the portion of the answer. Okay, from this paragraph, this is the answer. Now the second category is generating text. So generating text means like context generation, text completion, in fact code generation, paraphrasing, all these things are generating text. In context generation, so suppose a user asks him, give me some, write a story about an old man or something. So it is just a single prompt. Now depending on this, it will write the whole story. Suppose 100 word story, 200,000, depending on the what is the requirement of the user. So it is basically a generation task. Similarly, text completion. Now suppose there is a some text is given, and okay, we want to complete it. For example, in Google, everything in Google, if you search, type just one word, it will already predict the next word. Okay, now you want to write this something. And paraphrasing is also generating text. So like understanding and generating. So basically generating text also requires the understanding text, because without understanding, one cannot generate. First we need to understand what the user, what is the requirement of the user. After understanding the prompt, then only generation portion happens. So these are like question answer generative, like for example in chatbots, dialogue generation, summarization task, machine translation. These all types of task requires understanding as well as generating text. So like question answer generation or dialogue generation. So it is in the chatbots, like it is a turn wise. User will ask something, and the chatbot will first read it, understand it, and then generate the answer. And then again the user will like ask the another question. So it similarly for summarization, first the system needs to understand what is written in the suppose 1000 words, and then it needs to summarize it in just 100 words. So for summarizing it in 100 words, it will have to generate and write from its own, means using its own language. So yeah, so Next is all right. Let's take a closer look at how chatbots and LLMs evolved over time. So all started with in the 1960s with the Eliza, which was the very first chatbot. So Eliza was like a party trick. So it was very simple and simple pattern matching act like a therapist. Just it will repeat whatever you say and rephrasing it. Just that. It wasn't that smart by today's LLMs and uh, today's chatbots, all those things. So they were not that they not smart, but they showed us like what machines could do. So jumping ahead, like in 1988 and 2000, we got RNNs. So RNNs were recurrent neural networks. So these were very big leap because they could process sequences of data like sentences by remembering some context, like history of the like whatever is said. They remember it, and then depending on that, they generate the text. So, but RNNs struggle to remember longer context. So, which led to the development of LSTMs. So, LSTMs are long short-term memory networks. So, LSTM were also like RNNs, but with better memory, which allowed them to handle longer text more effectively. They can handle it. So, it was like good for early chatbots and language tasks. But then in 2017, everything changed with the transformer model. So introduced by the Google. So not like the RNNs and LSTMs, transformer did not process text one word at a time. Instead, they process the entire sequence or even the large paragraphs in parallel. So this is what which made them faster and better at capturing complex relationships between the words. So the transformers opened the door for a like new wave of models. First, there were like birds, bidirectional encoder a representation of transformers. So which were designed to understand the context by looking at the words before as well as after the target word. So it is like the whole sentence will come into picture. They cannot predict the next word. Means they cannot generate text, but they can understand the text. So BERT became the go-to the task for the like understanding and classification of the text. But then came the GPT, like which is generative pre-trained transformer. So which mm, this GPT was different. Like it just turned everything in a different direction. Now it was not just about the understanding the text. Now it was about understanding as well as text generation. So first like GPT-1, it started small, and GPT-2, then it was better, and like it amazed everyone with its fluency. But GPT-3 was a massive leap. It has like 175 billion of parameters. So which made it capable of generating paragraphs, stories, and even codes. Like this was a very uh, big jump. So GPT-4, like this is more further this advanced um, in reasoning and understanding tasks. So like right now, like GPT is the best, and Llama and all these Bard, Dolly 2, so Falcon, these are like the best models today. First, let's see like what is next word prediction actually, which I'm talking about like text generation. So given a word, suppose bench. So bench, just give the word bench. Now the system will try to predict which is the next word, like which is the most probable word which will occur after the bench. So it is dependent on the conditional probability and the joint probability. So given the word bench, the system will predict um, that drinking word in the whole vocabulary has the highest probability of occurrence. So similarly, now given the words bench and drinking, now what should be the next word? It should be may. That is the probability. So kind of it looks like it is kind of deterministic thing, because model is already trained on uh, large amount of data, whatever it has seen, it has learned from it, and depending on that, it is making the predictions. So let's start with the first sequence to sequence model. So in 1990s, for natural language processing, this RNNs or the recurrent neural networks were designed to handle sequences of the data, like sentences or the time series information. So it was different from the traditional neural networks, which treat each piece of input independently. So RNNs are special because they have memory. They can remember the information from the previous step in the sequence. When the processing, like before processing the new one, it can remember. Like for example here, how are you? It is given sequentially. First to the encoder, this how is given, then it creates some hidden state, and then again it is processed similarly. So, for example, like it has two main parts here. This is encoder, like green one is the encoder and the blue one is the decoder. So encoder reads the input sentences and compress the important information into a fixed size vector. Like here you can say the above diagram. Here it is suppose the river bank. So since the system doesn't understand the English language or any language, it only understands the numbers. So this how is first converted into a vector of the numbers. So this is known as embedding. So now once it is converted into the embedding space, and then now the system will start processing and creating the hidden states and all those things. So the basically what encoder does, encoder reads all the information in the input sentence and compresses it into important information of at the end of this encoder, we will get a fixed size vector that is known as context vector. So what does this context vector do? It summarizes the meaning of the entire input sequence into a condensed form. Looks like actually it is in very high dimensional space. And then the blue one is the decoder. Decoder then takes this context vector and generates the output sequence, like translating the sentence or predicting the next word, any kind of task. So it generates one word at a time. For example, first it will using this context vector, fixed site context vector, it will first predict like I, and then this I is fed to the second cell of the decoder, and along with the hidden state, like the whatever it has already seen in the context. So it is like now the earlier words like how are you, I, now it is fed to the cell, and next word prediction is am, similarly, and so on. So yeah. So like these so basically, if you see that such type of architectures were used for the machine learning, machine translation, and the summarization and next word prediction, like it can do almost everything by sequential learning of the language. Now came the transformer. So before the transformers, so this transformer was introduced by Vaswani in 2000 et al. In 2017 by the Google. So before this transformer came along, we used these models called like RNNs, which we just looked earlier, for the tasks like other tasks like language translation, prediction of next word, or understanding sequences kind of thing. So RNNs are good because they can handle sequences of the data like sentences and remember information from previous words while processing new ones. But the problem is they are slow, especially when dealing with the long sentences. They process each word at a time. So if you have got a really big sentence, then they start forgetting the earlier words and cannot connect them properly to the later one. So basically this forgetting happens with the longer sentences. So it's like trying to remember what you were talking about after a long conversation. So people most of the time they don't remember, and these models will definitely don't remember. So then transformer came along and pretty much changed everything. These are like faster and smarter than the RNNs. So instead of just reading word by word like RNNs, transformer can look at the entire sentences all at once. So this means that they can understand the whole context of the sentences in one go. It's like reading the whole paragraph to get the main idea, or instead of reading one by one word and then trying to remember like what we read earlier. And because they process everything at once, transformer can be trained way faster. So how, like, why they can why they can see everything at one go and RNNs cannot? So the secret is the transformer has something, a mechanism known as it is based on the mechanism that is self attention mechanism. It is like a system where instead of looking at the word you are currently processing, the model looks at all the words in the sequence to figure out which ones are important. So, for example, in the sentence, suppose there is a sentence that the cat sat on the mat. So, the word cat is connected to sat, but maybe on the mat isn't that important to the word cat, but when predicting the next word. But the model figures out these connections using attention scores, which help you to focus most important words for making predictions. So, uh, so self-attention allows transformers to capture relationship between words, even if they are far apart in a sentence, which is something like RNNs struggle with. So if you have a long sentence, transformer can still connect the dots between the words that are very far away from each other, like the cat and the sat, even if there are several words, like there are very large number of words in between cat and sat. So the important thing is like a transformer don't need to process each and every word one by one. They can process everything in parallel. This means they can work very faster and efficiently. So RNNs, on the other hand, like they are just go step by step, with which takes a lot of time, especially with long sequences. So transformers just kind of took over only because of they can learn, like they can handle big chunks of the text, train faster, and connect information which are very far apart from each other, which RNNs can never do. So that's why you hear about like GPT, BERT, and all these things which are built on the transformers do the amazing things like text generation and language translation, like better than the old RNNs model. That's why they are like RNNs are outdated now, and transformers take the lead. So if we want to if we look at the architecture of the transformer, so it is like it has encoder and decoder. So encoder, there are several models which are based on encoder only, and there are several models which are based on decoder only, and there are several models which are based on both encoder as well as decoder model of the transformer. So for example, uh, Bert, Roberta, Albert, Distelbert, Electra, all these models are encoder only models. And models like GPT Neo, Llama, and other large language models are they are decoder only models. And few models like T5, BART, and a few more. So they are both like encoder as well as decoder. So basically, encoder-based models are good at understanding the text, and the decoder-based models are good at generating the text. And the encoder decoder can handle both the things. Actually, if these decoder based models are not just good at generating the text, they are also good at understanding the text. So like encoder decoder models means are that's why like these decoder based models are like leading in the for the large language models and like GPT, Llama. So we will later on discuss like why these decoder based models, like since encoder decoder models are also good at understanding and generating text, then people who only use the decoder based model. Why? So now encoder based model, coming to the encoder based model. So these are the these models are all about understanding the text rather than generating it. So they are like the brain that reads and understand the sentences, graphs, or like entire big documents. So these are like models, BERT, Roberta, Albert, Distilbert, Electra. All these models are these focus on interpreting the meaning of the text and understanding the text. So instead of generating new words like GPT, they work on processing the input text for classification and name entity recognition, comprehension based question answering, text similarity, doing all those things. So, for example, like Bert, if you take the example of Bert looks at the entire context of the word. So here, like by reading just the suppose it just reads all the whole sentence at once, and whatever sentence, like whole sentence meaning, like suppose I want to predict the word, there is a fill in the blanks kind of thing. So if the it is like I am, now there is a blank sum and assistant. So I the system wants to fill up this blank. So it will look at the I am a as well as the assistant. So it will look the whole sentence before and after. So that's why it is a like a bird, like bi-directional. So bi-directional, a bird, Roberta, all these things work on this strategy. So that's why they understand, since they look at all the words together, so they can understand the text much better and in just one picture. So these encoder based models are um, like training. We look at the training of these models. So these are trained on the mass language modeling. So what happens during training, some words, yeah, tokens in the input text are just randomly replaced with the uh, like mask. Some mask means generally we replace it by the minus infinity. And then the model is trained to predict like what are those missing words should look like by looking at the previous and the afterwards. So for example, here it is like I am a mask assistant. So the model job is to just predict like this missing word, fill in the blanks kind of thing. So by doing that, the model understands and learns like what actually, like how context affects the meaning. So now these encoder based models are used for a like, let's see like how on what task these encoder based models are good at. So like text classification. So this includes like sentiment analysis, like positive review, positive, negative, spam detection. Is this a email is spam or not? So the model is trained to classify text and the like it will uh, categorize it based on the understanding of those words in the sentence. Second is like named entity recognition. So this task involves identifying similar entities in sorry it is like specific entities in the text, like people, locations, dates, all these are um, entities. For example, if in a sentence like if you take sentence something like Albert Einstein was born at some place, like some place name, and in March and some date. So the model will identify that Albert Einstein is a person, that place, like some, I don't know where he was born. So it is like the place at which the name of the place and the date on which date he was born. So all these are like entities. To extract all these entities, the system has to read and understand like what this text is about. Similarly, for question answering tasks, like so the model is given a passage of text and question, and it needs to extract the right answer from the passage. For example, if you ask where was Einstein born, so the model will look at the passage and then extract that word, that place, exact name of the place, and answer. and text similarity, suppose text similarity. So this is like for checking how similar two pieces of text are. So basically, this is done by the semantic search. So semantic search means in a like finding in a document some similar means similar lines or similar text in the document which are similar to in a meaning to the query. So it is like semantic search. And the paraphrase detection. So paraphrase detection is like checking two sentences whether they have the same meaning or something like that. So for example, if you ask like what is the capital of the France and which city is the capital of France, so the model should recognize that both questions are asking the same thing. So this is like semantic search and paraphrase detection. Now, like one important thing to know about these models is that they often need to be fine tuning. They means fine tuning must be done for some for these specific applications. So models like BERT are pre-trained to understand language, but they are not ready to perform tasks like sentiment analysis or question answering right out of the box. So fine tuning involves training the model bit more on some specific task specific data set, and so that it can do better job at a particular task. So for example, if you want BERT to classify like sentiment, so uh, sentiment analysis, so you will have to show the labels like which sentiments are like what kind of like positive, negative, and train a little bit, at least fine tune on that particular type of data, like so so that then only the model will predict the uh, right label. And suppose if you want to question answer with the model, then you have to train it on the data set when it learns to extract the right answer from the given passage. So all these um, this encoder based models are very much dependent on the fine tuning task. Otherwise, they will not perform that well. So basically, these models are like expert readers, not generators. So they understand what is being said, and they will do some tasks depending like classify answer, question answer, and identify some entities. And but they cannot generate or create their own text. So the second category of the models are like the decoder based models. So decoder based models are like the transformer, the decoder only part. So these models are mainly used for the task where you need to generate the text. So things about like autocomplete, dialogues system like in chatbots, creative writing like generating some stories or something. So all these are like tasks. These are done by the decoder based models. So models like GPT, Neo, Llama, all these are examples of this kind of architecture. They work on decoder based only model. So their main job is to take some input or the prompt and generate the relevant text as output by one word or like one token at a time. Now, there are two types of these decoder based models. First one is the causal decoder only models, and the second is the non-causal decoder only models. So like at causal decoder only model generate text step by step, predicting the next word based on what it has already generated. So for example, if the input is I am a virtual dash dash, so the word is masked, and so it will predict the next word, like next word should be assistant, but based on the words before it, like I am a virtual, depending on the like predict this word depending on the given words. So it does not have the access to the future words. So this is the very important point here in the decoder based models, that and such type of like causal decoder only model. So they can't see what is the future words. They can only see the previous word. For example, in the encoder based models, if you look at like I am a mass assistant, so it is like for predicting this virtual word, these model can see both the, like if you say like this is the previous words I am a, and the future word is assistant, so it has the access to both the words. The model can see both the things and then means try to predict. But here what happens, only the previous words are visible to the uh, model for predicting the next word. So these models are like for things like auto completion, they perform very great in auto completion, creating stories, and because they are naturally follow a sequence, just like you would type a sequence like one word at a time, and then like let's say for example we type I am a virtual assistant, so like we know like what should be the next. So similarly, these are the causal decoder only model. And non-causal decoder only models, these model work differently. So they can see all text at once, meaning they don't just generate one word at a time in a sequence. In fact, they can consider the entire sequence of the word, which can be useful for tasks like translation and summarization, where the understanding the whole context is important or necessary. So they use like bidirectional. These are also like they can similar to that, they can uh, look at left and right side, and then predict the sentence. So but now how the question is like how these models are trained, these GPT based models, which are like which uses like GPT and GPT llama, these are based on. So basically everything depends on the how, what is the model type and what, how it is trained. So in order to decide whether it should understand, it will understand the language, or it will also generate the language. So the training method of the decoder only models are usually involve like something called autoregressive modeling. So this is like GPT is also trained on pre-trained using this training method, autoregressive modeling. So this just means that teaching the model to predict the next word in a sequence based on the words that came before it. So think of it like at an auto completion task when you are typing a message or searching query based on like whatever you have typed so far. So the model will predict the next word or the next phase, like depending on like whatever you have written or typed previously. So in causal decoder only model, the training follows the same idea, where the model learns to predict one word after another, using only the previous words in the sequence. So one important and good thing about this causal decoder based models is with autoregressive training is that they are really good at the zero shot generalization. This means they can perform very well on the new tasks or input like without needing additional fine tuning. For example, we earlier see in this decoder based models, like they require a large amount of fine tuning. If some specific task comes, we need to show the model like, okay, this is the task and something, and just fine tune it a little bit. But decoder based are very good in zero shot. Zero shot means no need of fine tuning, just give the prompt and it will uh, like give the answers without actually telling like without fine tuning, basically you can say. So for example, if you ask like model to write a poem, suppose, or generate just a story, or complete a sentence, so it can do just based on the knowledge it has already learned during the training. So yeah, means no need of fine tuning actually. So this is the one of the reasons, so why like these models GPT, and actually this is not just one of the reasons, this is the like main reason why GPT 3 4 are, these models are so powerful. They are not just trained for one specific task. Instead, they can handle a wide range of tasks without needing additional training. So simply by just understanding the pattern of the language from whatever they have seen, they have learned everything, and they can means give answers to perform the task in the zero shot setting. Now few models like, yeah, so these are the like encoder decoder based models. So like these models are good at understanding as well as generating the text. For example, T5, BART, all these models are both they can understand and generate text. So these have like two parts, encoder and decoder. So so they were these this encoder decoder based models were primarily designed for the machine translation task, but they can be used for summarization, question answering, text to text transformation, and other multimodal tasks. So actually, why they are not that popular as the decoder only models? Because they are computationally extensive. Computationally expensive, why? Because they have the encoder. So for since the if you look at the encoder models, so they need the entire chunk of data, means entire sequence of data, and they learn the embeddings and generate the some context vector. So this is like the whole task of the encoder they have to perform before this context, like which represents the crux of the information provided at the input. So it is like you have to, then context vector is provided as input along with other things. So at the decoder, now the decoder will perform its task. So an additional amount of like computation which is required for this encoder is required. So these models are not that popular. The most popular is the decoder based models for Llama GPT. So now, like how large these large language models are. So if you look at the large language models like BERT Large, which was introduced in 2018, it had 345 million parameters. Then came the GPT-2 in 2019. It had 1.5 billion parameters. Then GPT-3 uh, came in 2020. It had 175 billion parameters. Now, the GPT-4 launched in 2023, it had like 1.4 trillion parameters. Trillion means like very huge. So given this huge number of parameters and enormous amount of training data, scale of computation is like mind-boggling. If you compute like 1 billion computations, 1 billion computations means like, for example, multiplication or addition. So you should understand like how much time it will take for like LLMs like GPT. If humans start, or like if we start like 1 billion computations per second, so how much time will it take to train this model like GPT? So you can say like how many years? I just can't read it. Maybe something. So So such big computations for training the LLMs was only possible with the GPUs. So they have totally changed the game when it comes to the big computation. So unlike regular CPUs that can handle the task one at a time, GPUs can do thousands or even millions of calculations at the same time. So this makes them perfect for training models like large language models, which need to process like tons of data all at once. So why? Like because it can do everything in parallel. Parallelization is possible because after coming means after this GPUs came into picture. So when you are training something like GPT, there are trillions of parameters and huge data sets to work with. So it would take forever if you were like if you process all that on a regular CPU, it will like take forever. Like we don't know how much time. So but with the GPUs, we can break all those tasks into smaller chunks and then handle them in like parallel. So which basically speeds up the computation and do it in very fast. So for example, tasks like multiplying matrices. which are like super important in the neural networks. So this can be done on thousands of data points all at once, making it way faster. So without GPUs, like training models, Bird GPT and other, like it is not possible. Actually, it is impossible to train all those models without GPU. Cannot think of. So like why? Um, so like previous models, like which were based on like sequence to sequence tasks, like one word at a time. So we cannot parallelize these previous models. So like GPU had, we cannot parallelize and do the computation faster on the GPU by using this previous models. But after, when this transformer came, the architecture was such that because of their self-attention mechanism, we can like process all the computation at once. So now it was possible to divide it into like chunks of computations and use the GPU for like some computations and parallelize it in parallel. Like in parallel, it can do a lot of computation. So it was only because of the transformers that such big LLMs and big models were possible to train. So now the large language model. So coming back to this, so what exactly it does? So the large language models are actually not brains. These are just the next word predictions. So given user say, give me some idea for what to do when visiting Santiago. So assistant will start predicting after this, like after visiting Santiago, what could be the next word. So similarly, like suppose AI assistant has written like one option can be do to take, uh, could be to. So next word, given the vocabulary of the whole English words, which is the most probably depend on the weights. It has already learned weights because the pre-training, it has already been trained on a large number of data set. So it knows like which the occurrence of which word is most probable. So the objective function, how it is, what it learns. So the goal of such large language models is uh, to learn a model that can predict the next token based on the prior tokens. So for example, sequences x1 to xt, the probability of the entire sequences will be like joint probability of the x1, x2, like all the words or all the tokens. So joint probability of all the words or all the tokens will be the conditional probability multiplied by the prior. Similarly, uh, like it will, for example, given just nothing is given, so it will predict some x1. This is the prior probability. And then given the word x1, what is the probability of predicting the next word in the sequence, like x2? What is the probability of x2 given x1? And then probability of uh, x3 given x1 and x2. Now up to till like given x1 up to till xt. Now what is the probability of the next word, that is xt? So it is calculated like this. During training, the model learns to maximize this probability. All right, so now let's talk about something uh, like bit strange that happens with the LLMs called hallucination. So basically, uh, when like LLMs hallucinate, they give answers that sound really convincing, but are actually totally made up or incorrect. So it is like when chatbot tells you something that seems right, but when you double check or like cross check, it turns out to be false or just like plain random. It is just spitting out something. So this happens because the model is not actually thinking or understanding, because like humans do, because it is not a brain. So instead, it is just predicting the next word based on the pattern it has learned from the huge amount of text. So sometimes it gets things wrong or mix up the facts. So it's a big challenge, because even though the answers sound smart, they might not always be true. So it is something like researchers are working on it like very actively. So for example, if you ask this, this is a snapshot of the screenshot of this GPT. So I asked the question, how many employees are there in the Fujitsu Research of India? So it said like, okay, this FRIPL is headquartered in Bangalore, approximately 211 employees as of 2024, and something like AI machine learning, something he said. But this information is not correct. So the Fujitsu has not this many of employees, it has more employees. So now this is like, first of all, it might be because the web pages are not uh, so it is also giving this a company check and some references like from where it extracted this data. So it may not be updated, that's why it is like giving wrong answers. Or sometimes it just predicts the next word. You ask anything, and if you ask the give me the reference of some paper which has this kind of work, so it will just write some random reference of some random papers which even doesn't exist. So it is kind of like hallucinating. It will write something, but which may not be always true. So now how can we reduce the hallucinations in the LLM? So let's look how we can try to reduce the hallucinations by. So actually what happens, these models tell incorrect or uh, like made up stories or false information. These are the hallucination, as we already seen. So first is the like better training data. So if our training data is high quality, like more accurate, we feed the model more accurate and the uh, like different type of information, so it will come up with, like it will not come up with the wrong or the random answers. So it is like the source of the information, and the amount of training should be better. If it is like high quality data, then uh, it will not mix up things. And so another is like fine tuning. So like reinforcement learning from the human feedback, this is also very important, and fine tuning is also very important. So I have not so these are like, first I'll explain this fine tuning. So like fine tuning, like this is when we pre-train model and train it more on some specific task. So like reliable data. So suppose some proprietary data is there, and it has not. So suppose proprietary data, or some, suppose I will just give example of the software logs. So if like there are software logs and in the system, these are like company specific. People outside it doesn't have the access to it. So now since it doesn't understand, suppose the log errors and all those things, so it needs the fine tuning on that log type of data, so that it understands like what the errors in the log mean and all those things. So maybe after that, if you ask something about log related thing, it will not give the false answer. The second is like feedback, like human in loop, we can say. So reinforced learning with human feedback. This is like how the GPT is also after the pre-training. GPT 4 is also trained with like reinforcement learning with human feedback, where human sees the answer and tells like, okay, this is right, this is wrong, and then again give it back to the system, so that there is a feedback loop is maintained. So a human in loop kind of thing. So and there are like one important is like retrieval augmented generation, which we will also discuss in detail in the later slides. So the model doesn't generate answer from the memory books, but look up information from the like some source, some trusted source, or maybe non-trusted also, like some database. So this is like you give some uh, documents to the system, and it will go and extract the information, look up the uh, document, extract the important information, and then come back with the answer. So it is like retrieval augmented. And generation is, since these uh, means here LMs are also involved. So for example, I'll give you just one example. Suppose any organization, any company has some private data. For example, the information of the employees, salary of the employees, or something. So which we cannot disclose to anyone else, or large language models, because they are basically run on clouds, or maybe the data can leak, so it is like highly confidential data set. But we want to use the LLMs for the answers. And also, like, if we ask, like here we ask the specific question about the Fujitsu, the ChatGPT was not able to answer those. So how to make these LLMs work or answer to the queries which it doesn't know, or like which is kind of private data. So this is here, like retrieval augmented generation comes in picture. We can use this document and like this is a method. Okay, I'll discuss it in detail here. So like now we will see like how it reduces the hallucination. So like LLMs, for example, GPT. So these are dependent on like what they have learned during the training, but they have a way to look at the specific information they want to. So where this is like where a RAG comes in. So it suppose you ask a question or give a model a query like what is the latest on the climate change. So model will just go and search the knowledge database, and combine all the information, collect the information, combine the information, and create a more up-to-date response. So and then it will give it to the um, LLM and generate the answers. So basically, if you look at and the answers might be like correct. So if you look at here, like question, user asks a question. This is smart retriever. Smart retrievers will, since it does since the LLM doesn't have the information of the some private data set, so what it will do, it will go to a database which is private data set provided by the company. It will go and look up, like it is kind of like stack of books. So it will just go and check, read the books, okay, which one has this information, which is the most similar information, which book, as kind of. So it will retrieve that information, relevant documents, and then question and add this book. Suppose it picked out one book, it will add that book, and then it will give it to the LLM as a generator, and ask LLM to generate the answers depending on this question, and the answer is provided in this book. You have to, it will ask the LLM that, okay, look in this book, the this question answer is the answer of this question is given in this document or the book. So LLM will search the answers in this book and uh, use some like its own learned language, English language, make it a good answer, and then give it to the user as an answer. So now this is like RAG details of the RAG. So first we will like break it down in step by step so that we can understand it easily. So it is like creating a smart assistant. So like we have used chatbots, all these things on the private data set. So this is kind of something, a smart assistant, and which will not just guess, right? It doesn't do the guesswork. In fact, it will go and search the data and pick the correct information and then give the answer. So it reduces the hallucination actually of the LLMs. So first we need a bunch of documents here. This could be like anything, company's manual, uh, like FAQs, like question answers, which are most frequently asked, research papers, or like any kind of useful data which is private to the company. So this document will like this document hold all the facts and information which will model will refer to. So imagine you are building an assistant for a tech company. You collect all the user guides, product description, and internal reports. That is your knowledge base. So this is like documents. So the next step is to chunk these big documents into smaller, manageable pieces called chunks. So why? Because handling an entire book or the long document all at once would be too much for the LLM, and also it will exceed the context length of the LLM. So basically, LLMs have a fixed context length. Like you cannot give the suppose I want to ask ChatGPT, okay, I'll copy all the information of one paper that is like 12 pages length and give it to the chat GPT for summarization. So what it will say, it will not summarize it. It will say, okay, context length is exceeding. So give some smaller piece of information. It cannot process so this much of information. So it is like this is called the context length of the model. So it will exceed if you give big documents, the LLM's context length will exceed. So that's why we need to divide it into chunk of the data into chunks, like small pieces of information. Suppose, so like each chunk might be a paragraph or even like a few lines. So depending on the size of the document. For example, if you are working with a 20-page PDF, you break it into smaller sections like uh, features of product A and like how to troubleshoot error B, like kind of, or you can straightforward just two lines each. It means every chunk should be starting from the first word. Just take the 200 words and then make one chunk, then next 200 words make the other chunk. Similarly, you can divide. I mean, it is like user dependent, like how you chunk your data. The goal is just to make it in small pieces of information. So now each chunk is turned into a vector embedding. So think of it as a converting the text into mathematical expression. So the vector is a number of like high dimensional space. For example, we had showed earlier like in this slide. Yeah, so here like word is like suppose bank, river, every word is converted to some embedding like high dimensional space in some vector of numbers, because words has no meaning. The system can only understand the numbers. So this will convert into like vector of numbers in some high dimensional space. So these embeddings capture the meaning. Actually, they capture the meaning of the text. For example, chunks uh, about suppose customer support will have embeddings that are closer to each other. So like every customer support information will have like all the embeddings of the customer support data may have their embeddings. They are like very close to each other. And the chunks about the product specifications, so it will not be as close to the customer support, they'll be further apart. So it's like giving each chunk a unique fingerprint that reflects its content. So these embeddings are generated using uh, pre-trained models, so which are good at understanding text like BERT. And so popular embedding generation models people use are like BERT, sentence transformer, or like there are many OpenAI embedding models also, for which creates the high quality multi-purpose embeddings. So it is like since you have the information, you can use the encoder only models or the like BERT, which are good at understanding text. So it will understand and create the embeddings of it. And once these embeddings have generated, we need to store them somewhere we can search later. So now where to uh, store these embeddings? So here vector database comes in. Like it is a special kind of database designed to handle these embeddings, and uh, so that for a quick search they can be used. Like it will find the closest match very quickly. So it is designed in such a way. So it is not like traditional databases that work with rows and columns like tables or SQL and data sets kind of like tabular. So these embed like these database sorry these database like vector database are stores embeddings as points in the multi-dimensional space. Where you search for something, it finds the embeddings that are nearest to the query. So popular database like are there are many, so like to name a few, like Pinecone is one, Fairs and ChromaDB. So I generally use the ChromaDB. so I prefer ChromaDB. But like there are many available which are like cloud-based, and you can also use it on your system locally. So what it is actually, so it is like, think of just it is a giant kind of map, and where all the ideas are grouped together. So vector databases, after we create and save the embedding, so it looks like similar kind of ideas are grouped together like a clusters. So like in one cluster there will be some specific suppose given a topic ki customer support, so customer complaints, so it will create these embeddings will create a cluster at one place, and some other type of query, suppose some product description, it will create some cluster. So it will look like, if you try to visualize it, it will look like this key. Okay, so in this way, this vector databases store the embeddings of these chunks. So for example, the query, if you just try to, one more example I just want to give, key query is like reset password. So might match chunks like troubleshooting log. So like how to do the kind of like similarity search, if you want to do now, actually now you want to do the similarity search. So in this arrow, now this vector database is made, created, and all the embeddings of these chunks are stored. Now the next task is to do the similarity search. So how to do the similarity search? So suppose you have a question like, how do I reset my password? So the system will convert this question into an embedding, and just like the chunks earlier, so the embedding of the chunks were generated. Similarly, the embedding of the query is also generated. And then it performs the similarity search in the vector database. Like it will do the similarity search, like which chunks embedding as is most closest to the question embedding. So it is like what part of the document are most related to this question. So it is not just the uh, exact similarity, it is like a semantic similarity it is. So like it, because the system these embedding models are also they can understand the text. So suppose like bank of a river, so they can they understand like bank is like bank of a river, or bank of a like money where we deposit the money. So depending on the context, so such, if you want to do the similarity search, semantic similarity, they will try to understand that error. So if you write the error, it like it can also detect like which are the synonyms, or like kind of things. So it not just will look for the error, it will look for the words similar to the errors also. So generally people use the cosine similarity also. So like how similar embeddings are. So like now the task is to retrieve the chunk. We created the vector database, we created the mhm, embeddings of the query, and retrieve the now we perform the similarity search. Now the task is to retrieve the chunks. Like similarity search is done, suppose, so for after the similarity search, every chunk has got some weightage, like some is 0.9 similar, 0.9 90% similar, some is like 0.10% similar, something every chunk is uh, given some weightage. Now which document to retrieve? So it is like the top matching are pulled out from the vector database. So these chunks are essentially the most relevant piece of information from the documents that could help the answer the question. So let's say there are query matched 3 chunks. So if we look for the exact chunk, suppose we have an exact fact retrieval kind of query. So it has, suppose it matched the 3 chunks. To reset, for example, to reset your password, just go to the some setting page, and if you forgot the password, just click the forgot password, and password should be something this much of length, suppose 8 words, 7 words, something. So these three chunks, these are the top three chunks. If like top three chunks are retrieved because it has the most similar means the answers required for questioning the query. So now now the retrieved chunks are combined together and sent to the LLM or the GPT for the original question along with the original question, so that it will generate a final answer using that query and the combined information that is present in the chunk. So this time, like, LLM doesn't guess the pre-trained, it will not guess anything like pre-trained LLMs do. It will use actually the information which is correctly retrieved from the some database, and it is using that to make a response in good English. So it is like are correct, and the hallucination of the LLMs can be controlled in such a way. Thank you, everyone. So for today's session, this was my end slide. So
Thank you,
now
Dr.
I would like,
Supriya.
okay,
Thank you so much um, for accepting our invitation and sharing your expertise with us today. We are very grateful for your time and efforts. Thank you once again for an outstanding session. Thank you, ma'am.
thank you, ma'am. Thank you, Gargi, ma'am.
Thank you so much, ma'am. Audience
Thank
can
you, Rakhi,
ask
ma'am.
questions. If any audience want to ask anything, please raise your hands. We will unmute you. From the audience side, ma'am, there is a question. The hands-on session will be on Saturday, tomorrow. So I think we can have the practical implementation of the same in the next session. Ma'am will take the next session tomorrow at 10 a.m. So you can take the insights from there. We will provide the PPT, don't worry. Is there any question to be asked from Supriya ma'am, participants? I think ma'am.
Okay, no problem. Yeah.
Okay.
Thank you.
Thank you so
Thank you,
much.
everyone. Thanks,
Thank you, ma'am.
everyone.
Thank you.
Participants. So today we are just closing the 5th day of this FDP. And thank you all for your time and dedication. Regarding attendance, we are handling the issues you are facing regarding those who have attended and marked absent somehow. So we are just checking it out because we have to do one by one on the ATAL portal. So it is taking time. Thank you for your patience. And tomorrow we will have this session in continuation with this session by Supriya ma'am. So we will have a hands-on session on the same, the customizing large language models for the specific use cases. So please connect at 10 a.m. tomorrow. Thank you so much.